Okay, in our next chapter, chapter number 9, we will talk about solutions. Now, a solution is a homogeneous mixture of two or more substances. There has to be at least two, but there's no ceiling, no limit in how many there can be. Now, a solution will form when there's a sufficient attraction between the solute and the solvent molecules. Now, those terms, solvent and solute, are what make up a solution. The solvent is the substance that's present in the higher amount. In almost every case in chemistry, the most likely solvent will be water. And then the solute is the substance found in the smaller amount. So, for example, the image that's given here, you have a beaker filled with water and salt is being added to it. So that is forming a solution. You have a mixture of two or more substances, the water and the salt. And in this example, the salt is present in the lesser amounts. The salt will be the solute, and the water will be the solvent. Now, solutes can be either liquid or gas or solid, just like in the previous example with the grains of salt. They will be evenly spread out throughout the solution, and they will mix with the solvent so the solute and solvent have the same physical state. Another key factor about solutes, you can't separate them by filtration. For the beaker of salt water from the previous slide, you couldn't filter out that salt just by using a normal filter of any kind. But the way you can separate the two is by evaporation. If we were to take that beaker of salt water and evaporate the water away, the salt would remain behind. So that's how you can separate the two. It has to be by evaporation of the solvent. And solutes are also not visible, but they can give a color change to the solution in general. So going back to this image here, salt water tends to be cloudy. Even though you can't see the individual grains of salt, the presence of the salt as a solute gives the overall solution a very cloudy or very turbid appearance to it. So it does result in a color change, even though you cannot see the individual components. All right, here's a table of some common solutes and solvents, both in a gas, liquid, and solid. For gas solutions, a gas in gas. So for example, air is a very good example. Primary solute would be oxygen, solvent would be nitrogen, because nitrogen is present in the higher amount that oxygen is in the general air. For liquid solutions, a gas in the liquid, say soda water or household ammonia. So for household ammonia, the primary solute would be ammonia, and the solvent would be water. Say vinegar, this would be primary solute, and water, primary solvent. Seawater, sodium chloride or salt, with the solute, of course, water would be the solvent. So in almost every case, we're talking about a liquid solution. In most cases, not all, but in most cases, especially in chemistry and biology, the solvent will almost certainly be water. Now, water is probably the most common solvent found in nature, and it's a polar molecule due to the bond between the oxygen and the hydrogen. And the molecules that will form hydrogen bonds like this are very important in many biological compounds. This is a very commonly found type of bond found in biology in particular. All right, some solutions can have ionic solutes, and a good example of that is salt water, like we talked about before. Salt, the sodium chloride. These crystals will undergo hydration as water molecules surround each ion and basically pull it apart into the solution. So what you have here is the solid particles of salt, sodium chloride. When added to water, it will break that up into the sodium ion, sodium +1, and the chloride ion, chloride minus. So that's what's happening here. You're getting the separation of the solute, but what you're forming is ions, the positively charged sodium and negatively charged chlorine ion. All right, now we'll talk about solutions that have polar solutes. A polar molecular compound, such as methanol, which is really just a carbon surrounded by 3 hydrogen atoms, and that's joined to an hydroxide ion, or OH ion, is soluble in water because methanol has a polar OH group that will help form a hydrogen bond with water. Polar solutes require a polar solvent in order to form a solution. So here's how this would look. Methanol solute, and then you have the water solvent. So when you add these two together, you get the methanol water solution due to the hydrogen bonding. All right, next we'll talk about electrolytes, what's considered a strong electrolyte, what's considered a weak electrolyte, and what's considered a non-electrolyte. All right, for the first one, a strong electrolyte, this is a compound that will completely dissociate or break up 100% in water, and by doing so, it will produce a positively charged ion and a negatively charged ion. And these will form solutions that are able to conduct an electric current strong enough to power a light bulb. An example of one of these is one we've already talked about, sodium chloride or salt. When you have sodium chloride being broken down with water, it will completely separate, so every crystal is broken, forming either a sodium ion or a chloride ion. And these are a very, very strong electrolyte solution. Other than that, you have what's called a weak electrolyte. These will only dissociate slightly in water, so the compound will break up a little bit. Not all the atoms will break up. Some do, but most don't. So a good example of that is hydrogen fluoride. Added to water, some of it will break down into a positively charged hydrogen ion and a negatively charged fluoride ion, but not all of them do. Mostly the compound will stick together. That's why you'll get some ions here, some ions here, but for the most part, it doesn't really break up all that much. So this is considered to be a weak electrolyte. You still get some conductivity of electricity, but not that much. And lastly, non-electrolytes. These are compounds that will dissolve but as molecules in water. They don't produce any ions at all. So because they don't produce any ions, they don't produce, or they're not able to conduct an electric current. A good example of that is sucrose, which is a form of sugar. So a solid form of that being dissolved in water. All you get is sucrose being dissolved in water. Now it's an aqueous form of sucrose. It doesn't break up at all. There's no loss of any particles in any way, so it doesn't have a negative or positive charge to it, so it can't conduct an electric current. Alright, next we'll talk about solubility. Now, solubility is the maximum amount a solute can dissolve in a specific amount of solvent. Now, this is usually temperature sensitive for solutes, and the way this is written is it's expressed as a measure of grams of the solute in 100 grams of solvent, usually water. This is usually how you'll see it represented. The grams of that solute divided by 100 grams of water. Now, solutions that are unsaturated contain less than the maximum amount of solute. Some of it has broken down, but not all of it. So you can still dissolve more solute. So not everything has been completely broken down. It is unsaturated. Now, the opposite of that would be a saturated solution. A saturated solution is a solution that contains the maximum amount of solute that can be dissolved. It may have undissolved solute at the bottom of the container. And one thing that may also happen is in a saturated solution, you have the solute that will dissolve, but it may also recrystallize and then break down again, then recrystallize and break down again. So this is how that would look in an equation. Solute plus a solvent. It completely dissolves, so you get a saturated solution, but some of it may recrystallize to go back to here and then go back and forth. This is a reversible reaction. That's why you have the double arrows here. So we're getting comparing the two, unsaturated versus saturated. For unsaturated solutions, some of the solute has been broken down, but not everything. There's still more to be dissolved. And in a saturated solution, everything has been dissolved, and you may still get some crystallization, like you do here at the bottom of the beaker. So it may dissolve, then recrystallize, then dissolve, then recrystallize, on and on and on and on. But this has the most you can get. This one has only some of what you could get. Alright, now we'll talk about the effect that temperature has on solubility. Solubility will depend on temperature. Now, of most solids, the solubility will increase as the temperature increases. Any type of solid material, the higher the temperature, the more that you're able to dissolve away. And for gases, the solubility will go down as the temperature increases. Okay, in this chart here, you have temperature on this axis here, and then solubility on the vertical axis. So for, say, glucose, for example, as the temperature goes up, solubility gets much, much higher. Potassium iodide, a nice steady incline based on temperature increasing. And again, the solubility of gases will go down as the temperature increases. Right, here are some common examples. Oxygen here, carbon monoxide here, nitrogen here. As you can see, as the temperature increases, the solubility of each gas will go down. And that's true for every gas, not just these three listed here. But as temperature goes up, solubility will go down. Alright, now we'll talk about the connection between pressure and solubility. And a good way to explain this is what's called Henry's law. Henry's law states that the solubility of a gas in a liquid is directly related to the pressure of that gas above the liquid. And at higher pressures, more gas molecules will dissolve in the liquid. So when the pressure of a gas above a solution goes down, the solubility of that gas also goes down. So example that's given here, a typical can of soda, you have carbon dioxide under high pressure because it's closed. So you'll have more gas dissolving in that liquid. But once you open it and that pressure gets released, it's going to be much lower pressure on the liquid because the pressure of the gas above it has decreased. Alright, next we'll compare soluble versus insoluble ionic compounds. Only ionic compounds that contain a soluble cation or anion are soluble in water. In an insoluble ionic compound, the ionic bonds are way too strong for the polar water molecules to break apart. So we can use the solubility rules to predict whether or not an ionic compound would be expected to dissolve in water or not. Alright, here's a table for the solubility rules for ionic compounds in water. For positive ions, say lithium, sodium, potassium, rubidium, cesium, and ammonium. An ionic compound is soluble in water if it has either one of these positively charged ions or if it has negative ions. Now, if an ionic compound does not have at least one of these in this table, it is most likely insoluble because the ionic bonds are just too strong for the water to break apart. Alright, next we'll talk about a property called molarity. Now, molarity is the moles of a solute per liter of solution. And it's usually written in this way. Capital M for molarity. Moles of a solute per every liter of solution. A solution of sodium chloride is defined as having 1 mole of sodium chloride per 1 liter of that solution. Alright, next we'll talk about some various properties of solutions. The image here is antifreeze being poured into a radiator, and the compound that's found in that is ethylene glycol. This will help form an aqueous solution that will help lower the freezing point. This will help form a solution that actually has a freezing point that's lower than water. That's why it's called antifreeze. It takes a lower temperature in order for it to freeze. For the learning goal for this section of the chapter, be able to identify what is a solution versus a colloid versus a suspension, and describe how the number of particles in a solution will affect that solution's freezing point and boiling point and the osmotic pressure of the solution. Next we'll contrast solutions and colloids. Solutions will be transparent. You cannot separate the components and will contain small particles or ions or molecules that can't be filtered through a semi-permeable membrane. A good example of this is the salt water that we've been talking about this chapter. You can't separate the salt from the water. The only way you can separate the two is by evaporating the water. That's not a filtration process, that's evaporation. Now that compared to colloids, a colloid will have medium-sized particles within the solution. It also cannot be filtered, but it can be separated by a semi-permeable membrane. And in this table there are some examples of some common colloids. Say cheese, butter, milk is another good example of a colloid, shaving cream, soap suds, so on. Next we'll talk about suspensions. Suspensions are heterogeneous and non-uniform mixtures. These will have very large particles that will settle out of the solution. When the solution is not moving or when the solution is standing, not being stirred, the larger particles will settle down at the bottom. These can be filtered, and they must be stirred in order to remain suspended. Once you stop stirring, say a glass of water where you add dirt to it, if you keep stirring, they will all mix together. But once you stop stirring, the dirt will settle down to the bottom of the glass, or bottom of the beaker. That is a suspension. Other examples, platelets that are found in blood, muddy water, and calamine lotion. Alright, next we'll talk about freezing point lowering and the boiling point elevation. When a solute is added to water, physical properties can change. And also the vapor pressure above the solution can go down, the boiling point can increase, and the freezing point can also decrease. Now, these types of properties are called colligative properties. They only depend on the concentration of the solute particles of the solution. So the higher the concentration of the solute, the higher the impact you'll have on the solution in general. Alright, first we'll talk about vapor pressure lowering. Increasing the concentration of the solute particles in the solution decrease the number of solvent particles at the surface of the solution. This will prevent some of the solvent particles actually leaving the solution. So let's say this example here is one we've talked about before, the water and then adding the salt to it. So in this beaker would be just a pure solvent, just a pure water. And in this beaker here we have the solute plus the solvent. So for our example, adding the salt to the pure water. And by doing so, since you're adding the solute to the solvent, you're actually lowering the vapor pressure. And by doing so, this also prevents some of the particles of the solvent from escaping the solution. Alright, next we'll talk about boiling point elevation. Increasing the concentration of the non-volatile solute particles in a solution will raise the boiling point of that solution. And because you're increasing the concentration of the solute, that will actually lower the vapor pressure and also will increase the boiling point of that solution. Alright, somewhat related to that is the freezing point lowering. And a good example of this is when you add salt to a road or, say, a sidewalk or a driveway that's covered in ice. And by doing so, that ice will melt. And what you're doing here is actually lowering the freezing point of the water. So instead of freezing at 32 degrees Fahrenheit, it may now freeze at 28 degrees or so. So it takes a lower temperature in order to freeze. An example that we've seen before, or we saw earlier, adding the antifreeze to the radiator. By adding the ethylene glycol to the water in the radiator, you are forming hydrogen bonds between the water and the ethylene glycol, and because of that process, you are lowering the freezing point, which is why it's called antifreeze, and also you're raising the boiling point of that solution. Alright, now we'll talk about particles in solution. A solute that is a non-electrolyte will dissolve as a molecule. We talked about this earlier. Whereas a solute that is a strong electrolyte will entirely break up as ions. So for example, the solute antifreeze, ethylene glycol, C2H6O2, is a non-electrolyte, so when it dissolves in water, it just dissolves as an aqueous molecule. So 1 mole of ethylene glycol in a liquid form, when it's dissolved in water, will just become 1 mole of aqueous ethylene glycol. It doesn't break up at all. So that's why it's a non-electrolyte. An example of a strong electrolyte that we've talked about previously, sodium chloride, NaCl. When that's in water, it will completely dissociate. So you have the sodium ions, which are positively charged, and you have the chloride ions, which are negatively charged. So this breaks up completely compared to ethylene glycol, which doesn't break up at all. But when you're comparing the number of moles in that solution as it breaks up, 1 mole of sodium chloride will break up into 1 mole of sodium ion and also 1 mole of chloride ion. You don't get a 50-50 split. You don't get half a mole here and half a mole here. You get 1 mole of each individual component of that solution. So 1 mole of sodium chloride in solid form will actually give you 2 moles of particles in solution because you have 2 ions being formed here, and here. Alright, now we'll move on to osmosis. Hopefully you remember this concept from general biology. This is the movement of water across a semi-permeable membrane. And here's an example of how that would look here. This is a beaker, and it's divided in half by the semi-permeable membrane. You have these yellow circles here are the solute. In this example, they're going to be sucrose. And when you have a higher concentration of solute on this side of the membrane versus this side, water will always rush toward the higher concentrated side in order to balance everything out. That's a big theme in nature, is to become more stable, become more balanced. So there's too much more sucrose on this side of the membrane than there is here. So water will leave here to go across the membrane here to balance it out. And when that happens, this water level on this side will drop, and the water will keep moving until there's an equal concentration on both sides of the membrane. A nice equilibrium is what nature is always striving for, a balance. We'll move on to osmotic pressure. Now the osmotic pressure is equal to the pressure that would prevent the flow of additional water into the more concentrated area side. And of course the osmotic pressure is greater as the number of dissolved particles increases. In order for this water to be slowed down from going from here to here, the osmotic pressure needs to be higher, basically to put the brakes on the flow of water across the membrane into the higher concentrated side. Alright, next we'll talk about solutions that are either isotonic or hypotonic or hypertonic. And those concepts are very important when it comes to biochemistry in particular. Because cell membranes in biological systems, like human cells, are semi-permeable, osmosis is an ongoing process. It doesn't just happen once and it's over. It's constantly going on. You have water moving into a cell and also water moving out of a cell. So the solutes in biosolutions like blood or lymph or interstitial fluid or blood plasma all exert some type of osmotic pressure. And most IV solutions that are used in hospitals are going to be isotonic solutions. And iso means equal. Isotonic solutions exert the same osmotic pressure as the body fluids. Now solutions can either be isotonic, hypotonic, or hypertonic. And those terms reference the concentration of the solute versus the solvent. And what you want is an isotonic solution here. And the common example that's used to represent these 3 situations are red blood cells, as what these 3 are. In a normal, balanced situation, there's no net movement of water into the red blood cell or out of the red blood cell. There's water moving in and out, yes, but the net movement is 0. the amount that goes in equals the amount that goes out. So there's no change in volume there. So the red blood cells remain their normal shape and are able to function. Now, if a red blood cell were put into a hypotonic solution, the blood cell fills and fills and fills with water until it eventually pops like a balloon. There's only so much you can fill any kind of structure. It will eventually rupture. And when that happens, the cells are dead and they can't function. And the opposite of this is a hypertonic solution. The red blood cells will shrivel or crenate. By doing so, they become non-functional. So this is the situation that you do want, isotonic, but you don't want either one of these. In both of these situations, these cells will eventually become non-functional and then die. Right, in the hypotonic solution has a lower solute concentration than the red blood cells. Hypo always means lower or less than. So there is less solute in the solution than there is in the cell. And the way you can predict what direction these cells or the water moves, the water will flow toward the hypertonic side. So in this situation, the cell is hypertonic, the solution is hypotonic. So water will leave the solution and enter the cell. But when that happens, the cell will fill up with water and eventually will pop like a water. And that process is called hemolysis. Hemo because it's a blood cell, and lysis means to rupture or to break open. Okay, the opposite of that situation, hypertonic, the solution has more solute than the red blood cells do. Water will leave the red blood cells and enter the solution. But when that happens, these cells will shrivel up, a process that's called crenation. If that happens, the cells become non-functional, and then they will die. This is the same thing as if you ever were to put salt on a snail or on a slug. There's more salt outside of that snail's body than there is inside of that snail's body. So water will leave the snail in order to balance it out. But when that happens, the snail will shrivel up and then die. It's the same process here. So the situation that you do want the red blood cells in is an isotonic solution. There's no net movement of water. So the cells are able to stay their normal shape and be able to function normally. If they're a hypotonic solution, they will eventually be ruptured and they can't work. If they're in a hypertonic solution, they will eventually shrivel up and then die, and then they can't work. Now we'll move on to the process of dialysis. In dialysis, you have solvent and small solute particles will pass through an artificial membrane, basically functioning as an artificial kidney. The larger particles are retained inside and are filtered out of the blood. And so during dialysis, the products that are retained are common waste products, excess water, toxins, urea, and so on. The things that your body does not need or want inside it, that the kidneys would normally function or normally filter out, dialysis do that for you. Thank you for watching our newest video on our crash course in chemistry. We'll have new videos in this lecture series every Monday and every Friday of each week. So stay tuned for our next video in a few days. And don't forget to subscribe to this channel so you can be notified of when our new videos are posted each week.